In this video, I further explain denoising diffusion models. Given a distribution X0 sampled from Q, a forward noising process Q produces a latency from X1 to Xt by adding noise at a time t with the variance beta t. The conditional joint probability of X1 to t is defined as here, where Q is a transition. This is the mean and this is a variance. The noising and denoising processes are explained here. Given a large T and a schedule of beta T, the latent Xt is close to anisotropic Gaussian distribution. If the reverse process transition Q is known, starting with a sample Xt from a normal distribution, the reverse process P theta can generate a sample X0 from Q. A neural network is employed to approximate P theta through the mean mu theta and the variance sigma theta as shown here. Combination of the forward process Q and the reverse process P theta is a variational autoencoder as shown here. The model training is performed by optimizing the variational lower band on negative log likelihood. This likelihood and this lower band, where L0 is prior, LT minus 1 and LT are KL divergences. L0 is computed by estimating the probability of P theta into 56 color beams. LT minus 1 is a KL divergence between forward and reverse Gaussians, which can be estimated in closed form. LT is independent of theta and close to 0, since Q is close to P if a forward noising process adequately denoises the data distribution X0. Forward noising process samples an arbitrary step of noise latent directly, condition on the input X0 by defining alpha t and alpha t bar. The marginal alpha latent xt is written as here, where xt is here. And E is a normal distribution. We can use the variance 1 minus alpha t bar of noise to define the noise schedule is that of beta t. The forward process posterior Q is computed by using this formulation, where beta t tilde and mu t tilde are explained here and in this figure. Computing the lower band L becomes estimated key error divergence, LT minus 1. The training objective of denoising diffusion models is to compute the sum of independent terms LT minus 1 in the lower band. This formulation is used to sample Xt from the forward noise process, and then LT minus 1 is estimated using the forward process posterior Q and the reverse process prior P theta. The lower band L is estimated by the expectation here for randomly sampling time steps t. A new network is applied to predict mu theta in the prior. However, to generate the accurate result, the neural network is applied to directly predict the matching score E theta through the following reparameterization here. The denoising matching score loss function L is defined as here. For more details, please check with these references. Thank you.